I want to start this update by saying that I've had a few people tell me that I have to measure the input power at the batteries or power supply, whichever I'm using. The problem I have with doing that is whether I use the oscilloscope with DC coupling or use the input volts and amps displayed on the power supply. The input amps are way too high for the fuse I'm using. I discovered this by loading the relay contacts at about their maximum amp rating, and I discovered that measuring input with an oscilloscope using ACRMS, I get input amp readings very close to the size fuse I'm using, which is a 7.5 amp fast-acting fuse. But to try and satisfy those skeptics, I started looking for a way to prove beyond any shadow of doubt the gap generator does produce more power than it takes to operate it. So with some recent test results, I'm going to demonstrate that now. The first thing that I want to demonstrate is the input per power supply only. The first test I want to look at here was done on 2/26/17 at 1442. Had two lights and two 1500 watt heating elements. These are forklift lights. No full wave bridge rectifier. Had 26.61 average watts over unity. The input volts was 36 and the amps was 9.9, yet it ran on a 7.5 fast-acting fuse. The next test was done that same day at 1446, and it had 12.95 average watts over unity, and it had two lights and one 1500 watt element. And the voltage on that was 36 input times 6.5 amps. But see, we reduced the load here way down, and no problem for it to run on a 7.5 fast-acting fuse. The next test we're going to look at was done on the same date, 2/26/17 at 1501. Had an average watts over unity of 4.12. Two lights and two 1500 watt heating elements. We used a full wave bridge rectifier. The input volts was 36 according to the power supply. Input amps 9.3, yet it ran on a 7.5 amp fast acting fuse. The next test was done at 1504. And it had minus 6.32 average watts over unity. Fell a little short there. That's per the power supply. I had lowered the load, had two lights, two forklift lights, and one 1500 watt heating element. Again, no problem here, 36 volts input and 6.2 amps, running on a 7. The next test was run on 3/25/17 at 9:50 a.m. Had an average watts over unity of 16.47 per the power supply. This time we used two lights and one 1500 watt heating element. That's two forklift lights. No full wave bridge rectifier. Here we had 36 volts times 9.8 input amps. Now that certainly wouldn't run on a 7.5 amp fast acting fuse. Now in this next test, ran on 3/25/17 at 9:54 a.m. We had 13.01 average watts over unity per the power supply input, and I reduced the load here. I had one forklift light and two 1500 watt elements. So I guess I increased the load. One light and two 1500 watt elements. And we had 36 volts input by 8.5 amps. And again, it ran on a 7.5 fast acting fuse. The next test was done on 3/25/17 at 10:04 a.m. Per the power supply, it produced 5.1 average watts over unity. Had two lights, forklift lights, and two 1500 watt heating elements. The input voltage was 36 and the input amps was 9.4, and it had a full wave bridge rectifier. Now it ran on a 7.5 amp fast acting fuse. Now the next test was done on the same day at 10:07 a.m. Had an average watts over unity at 8.04 per the power supply. I reduced the load down to one light and two 1500 watt elements. And according to the power supply, it had 36 volts and 8.1 amps. And yet it ran on a 7.5 amp fast acting fuse. The next test was done on 3/25/17 at 9:29 a.m. Per the power supply, it had 10.59 average watts over unity. Now this time I used a different coil with a different core. It had 29.8 ohms coil with a 2-inch core. We had two lights and two 1500 watt heating elements. No full wave bridge rectifier. And again here, 36 volts input per the power supply, 9.7 amps input, yet it ran on a 7.5 amp fast acting fuse. The next test at 9:34 a.m. we had 2.32 average watts over unity per the power supply. Same setup, except I reduced the load, had one light, one forklift light, and two 1500 watt elements. And again, the input volts from the power supply was 36 and 8.4 amps. And yet it ran on 7.5 amp fast acting fuse. Now let's look at the last two tests that I did. On 3/25/17 at 9:41, we had an average of 2.28 watts over unity. That's per the power supply input. Had two lights and two 1500 watt elements. And like before, we had 9.3 amps coming in from the power supply. Yet it ran on a 7.5 amp fast acting fuse. Immediately after that test, I did one at 9:44. And it had an average watts over unity of 5.3 per the power supply input. I reduced the load here. I had one forklift light and two 1500 watt elements. But here it says that we had a 8 amps input from the power supply, and yet it ran on a 7.5 amp fast acting fuse. With the exception of one test done back on 2/26, and we'll look at it right here. Right here. That's the only one that fell short and wasn't over unity. But I adjusted the load and everything, so everything else, checking at the power supply input or battery input, as you want to say, everything else is over unity. It might not be over by much, but it's still producing more power than it takes to operate it. If it can be determined that checking input to the gap generator using the volts and amps on the power supply is not accurate, this device is way over unity. I think this should be determined by an independent expert in the electronics or electrical field. Here you see the linear version of the gap generator. I'm going to demonstrate the changing of the polarity in the coils and what takes place when that happens. Here you see the left coil of the linear version of the gap generator. Note the N on the core of the coil. This coil has magnets attached to the other end of the core. The N, or north side, of those magnets are the side that's attached to the other end of the core. Here you see the piston with the magnet's north side pointed toward the left coil. With magnets, like poles repel each other, and opposite poles attract each other. With one exception, everything I've said concerning the left coil is the same for the right coil. That exception is, on the right side, the south side of the magnets are utilized. Using a magnetic pole identifier, I'm going to demonstrate how the polarity is changed when the coil is energized. When in operation, both coils are energized and de-energized at the same time. When the green light comes on, that means I have energized the coil. The N, or north side of the left coil, is changed to S, or south. Now there I energized the coil again. There it did again. The first thing I'm going to do is demonstrate how easy the piston is to move back and forth. I even have a servo motor attached that I use to determine the output by the piston action only. I then will be energizing the left coil only, and watch what happens. At the very end, I'll energize the coil and keep it energized. This same process is happening in the gap generator with no moving parts. I want to go over 4 tests done on the gap generator with no moving parts on February the 26th, 2017. Each test in the spreadsheet, I have the results in an as recorded state, an input per the oscilloscope, an input per the power supply. Each test was done in amplification and neutralization mode. 2 of the tests were done with no full wave bridge rectifier. And 2 of the tests was done using a full wave bridge rectifier. All these tests were ran on a 7.5 amp fast acting fuse. And they were done checking AC in and DC out. Now if I check DC in, the amp readings are way high, up around 12 or 13, and there's no way it would run on a 7.5 amp fuse. And this has what I call a bidirectional circuit, which on an oscilloscope, if you're checking DC, it includes all AC. And using AC is the only way I could get the amperage to come out to where it's anywhere close to a 7.5 amp fuse. I mean, this thing will operate on a 7.5 amp fast acting fuse. So that's why I chose to do the test this way. I've increased the magnification so we can read these results a little better. And you'll notice right here at the top, it says more load equals better performance. And it does. The power supply was set to 36 volts in all tests. And here on the first test we have in the as recorded state. And you can see 73.57 average watts over unity with 124.24% unity. Now let's move over to the middle section where we can see it pretty good. This is per the scope input, the oscilloscope. It will give you the AC RMS there, volts and amps. So it had 68.74 average watts over unity with 122.3% of unity. Now let's move over here. Now here's the one where you really want to concentrate on. This is input per power supply. This would be DC in, and using the volts and amps on that meter, on that power supply meter. And right here it is, 36 times 9.9 equals 356.4 input per power supply. So I entered that right here. And the calculations came out, it was still 20.61 average watts over unity with 105.78% unity. I don't remember if I stated or not, but these tests were done with 2 lights and 2 1500 watt heating elements. So let's go back over here on this side. Now let's come down to the next test. I'll get it situated here in a second. There we are. Anyway, this test was done with 2 lights and 1 1500 watt element. So a little change in the load here. And as recorded, we had 41.8 average watts over unity with 120.37% unity. Now let's move over and get the center one. Per the scope input, 39.2 average watts over unity with 118.87%. Now over here with the input power per the power supply. We're still at 12.95 average watts over unity with 105.54% unity. So you can see with the drop in the load what kind of an effect it has. Now let's look at the tests that were done using a full wave bridge rectifier. So let's go over here to the left. And as recorded, with 2 lights and 2 1500 watt elements on the output. As recorded, 54.88 average watts over unity. That's an 119.32% of unity. Okay, per the scope input, 51.16 average watts over unity with 117.78% of unity. Now, looking at the input per the power supply, and that would be, like I said before, DC. We're still at 4.12 average watts over unity. Now we do have a drop in power by using the full wave bridge rectifier. I want to think it was 6.8% or something of that nature. Now let's go back over here and let's go down to down here in the as recorded with 2 lights and 1 1500 watt element. Got 2 lights and 1 1500 watt element. And as recorded, we're at 35.59 average watts over unity. Then per the scope input, we're at 34.15 average watts over unity. 117.81% of unity. I do have all these figures down in here at the bottom of these you can take a look at. Now we come over here. Per power supply input, we fell a little short. We're minus 6.32 watts average watts of unity. So we're not quite there. So by decreasing the load, this is what happened. But we keep that load increased. Here's 2 lights and 2 1500 watt elements, and you're still over unity. Now back at this statement right here, more load equals better performance. And I think these tests have demonstrated that. Also, I can increase the voltage up to, I'm at 36, if I can go 42, I get better results. If I go to 46, I even get a lot better results. But with the relay that I'm using, it just will not take the load. So if I had larger relays, I could increase the load or increase the voltage, or both, and get a lot more output. And when you look at this right here, again, this test over here, per power supply input, if we were, say, at 40 volts and put 3 1500 watt heating elements, this would go way up. Now in my mind, there is no one can argue with this thing whether or not it's over unity or not, because this is measuring DC in and DC out. And pretty much speaks for itself. These tests were done on 3/25/2017. They're identical to the test done on February the 26th, 2017, with one exception. And that exception is, I have changed the load on the output side. The change is very slight, but it makes a big difference in the outcome. Like the test done before, we have it in the as recorded state, and per the scope input, and the input per the power supply. We have it not using a full wave bridge rectifier. And we also have tests doing it with a full wave bridge rectifier. In the first test, done at 9:50 a.m., we showed 73.23 average watts over unity in the as recorded method with no full wave bridge rectifier. And then using the scope input, we had 67.51 average watts over unity. Now using the input per the power supply, we had 16.47 average watts over unity. And again, this was with no full wave bridge rectifier. This test was done using 2 forklift lights and one 1500 watt heating element. And it was done using a 7.5 amp fast acting fuse, as all tests this day will be done. This test was done at 9:54 a.m. on 3/25/17. And we used one forklift light and 2 1500 watt heating elements. And as recorded, we had an average watts over unity of 61.4. Using the scope input, we had 57.65 average watts over unity. Now using the power supply input, we had 13.01 average watts over unity. Now this test was done at 10:04 a.m. on 3/25/2017. And we're using a full wave bridge rectifier, 2 forklift lights, and 2 1500 watt heating elements. As recorded, we had 58.17 average watts over unity. Using the scope input, we had 52.89 average watts over unity. And using the power supply input, we had 5.1 average watts over unity. This test was done at 10:07 on 3/25/17. Again, a full wave bridge rectifier. This time the loads are different. We had 1 light and 2 1500 watt heating elements. As recorded, the over unity average watts was 54.49. Using the scope input, we had 50.59 average watts over unity. Using the power supply input, we had 8.04 average watts over unity. These tests were done on 3/25/2017 and done with a 2-inch diameter coil. The ohms of the coil is 29.8. Some of the tests are done not using a full wave bridge rectifier, and some are done using a full wave bridge rectifier. This test was done at 9:29 a.m. on 3/25/17. No full wave bridge rectifier. Has 2 forklift lights and 2 1500 watt heating elements. As recorded, the average watts over unity is 75.25. Using the scope input, the average watts over unity is 70.89. Using the power supply input, the average watts over unity is 10.59. This test was done at 9:34 a.m. on 3/25/17. And it has 1 light and 2 1500 watt heating elements. That's 1 forklift light. And no full wave bridge rectifier. And as recorded, we had 62.05 average watts over unity. And input per the scope, we had 58.13 average watts over unity. And per the power supply input, we had 2.32 average watts over unity. This test was done at 9:41 a.m. on 3/25/17. And we're using a full wave bridge rectifier. 2 forklift lights and 2 1500 watt heating elements. As recorded, 60.99 average watts over unity. And per the scope input, 56.62 average watts over unity. And using the power supply input, it's 2.28 average watts over unity. This test was done at 9:44 a.m. on 3/25/17 with a full wave bridge rectifier, and it has 1 light and 2 1500 watt elements. In the as recorded mode, we had 53.16 average watts over unity. Using the scope input, we had 49.55 average watts over unity. And using the power supply input, we had 5.3 average watts over unity.